you. Good morning. My name is Jean-François Côté, and we'll talk about the architectural modeling for upscaling tree and plant level attributes across forest landscape. So in this presentation, we'll see how an architectural model, carefully calibrated for some environment, can help you upscale models developed at different spatial scales. For instance, the relationship between core attributes and tree structure, and how to upscale this structure at plot level and the landscape level. Our primary instrument is the TLS. The primary instrument is the TLS, so we can get the full tree structure and of course the plot structure, but to get the correct geometry and topology, we go with architectural modeling or QSM, but to set different expression for the same thing. And in this case, for this environment, this case study, we use L-Architect, which is an old model, but it was developed for a boreal coniferous species. And it's quite robust, a little bit less accurate than other QSM, of course, but it was more robust for the needs. It takes TLS scans of individual tree combined with growth rule and information about the total amount of foliage into tree, for example. Into the crown, so you can reconstruct the 3D structure of your conifer. And then all our test sites or experimental sites were located at in Newfoundland, is the eastern-ish province in Canada. So it's dominated by balsam fir and black spruce. It's for environment as well. Those are permanent simple plots, so you cannot touch it. So there were a lot of data sets taken from the inventory, but additional like wood fiber attributes that were taken from trees outside these PSPs, and the scan of the individual trees were also taken on those trees that were core outside the PSP. So a subset of those trees were scanned, 200 trees, and we had collected tree map location on PSPs. To be able to reconstruct the plot structure as well. So first thing, we validated actually L-Architect the individual tree structure with tree fir, tree spruce, the structure measurement on the structure, so we were able to calibrate also the different variables in there, so we were able to extract different attributes linked to stem profile, crown geometry, distribution of materials, all those kind of things. At top level, in this case, we have the library of tree scans, and we have inventory data from for the tree position, for example. So at each tree on the plot, we selected like a lookup table of tree scans of the best fit, and used this point cloud as input to L-Architect to reconstruct the 3D structure and position the tree model in the plot. The problem was difficulties to get really a pretty good validation because the amount of measurement, or descriptive measurement was unthinkable at the time. And so we decided to get the validation through a virtual environment, which means that those plots reconstructed with tree scans served as reference data. And we generated, with independent methods and everything, a second generation plot that were able to compare with the reference one in a true value environment. It's good to go from the tree to plot, but to get to the landscape level, we developed a kind of a strategy similar to the lookup table for tree scans. We rely mostly on the huge library of model trees. So in our case, we have reconstructed more than 1,600 trees with the architects. So we put it in our model trees and using some input from either in situ measurements or above canopy, high spatial resolution remote sensing. Here we use DVH, height, and the crown protected area. So using these three inputs, we checked for each tree detected in our library of tree model, the best fit, and we copy the position, and we get our surrogate ground plots or ALS plots, depending on the input. So the virtual environment allowed us to compare tree per tree different social attributes. So normally we fit quite well on most attributes, below 50% on NRMSC, strongest case on the age, but not sleep area height. Challenging were mostly height life crown and crown asymmetry. At the lot level, where of course we average out something, so we're able to compare two stronger cases with the number of winches, or not AI or some things. Moderate relationship with crown-based height, crown width, and weaker height right crown and crown asymmetry. So those were the two more difficult to deal with at the moment. Just quickly, with the input measure from our simulated airborne LiDAR data, so we derive the DVH, height, and crown projected area. Same kind of observation, same kind of pattern, it's just that the number were a bit lower because of the uncertainties with the main input at the beginning. So we did that for the structure, so we upscale from the tree to the top to possibly the landscape, because we can reconstruct every tree iteratively over large area with that technique. So we wanted to use the architectural model to link core attributes with tree structure, but using this all fine scale structural information and improve our architecture that we have built before. So at the tree level, we just focus on the structural attribute. We know that species is the main factor. We know that environmental data drive some of the wood fiber attributes, but here we really focus on the structural variables to see if it's good to have this kind of information. So we have at tree level 22 predictors. We look at the variable importance. Some fine scale structure attributes just showed up in the models. So. And three-level model, we tested 4 different statistical approaches: 2 parametric, 2 non-parametric, stepwise regression, best subset, coniferous, and partial discrete. The parametric one had some issue with the regression analysis at the end, but it wasn't that bad actually. Sorry. But just for the sake of it, partially square, we were able to estimate the variance between 12 and 56%. We do the same thing at plot level. 29 predictors, no species, nothing else. The same statistical approach, just for the sake of it, partially square between 5. The 5 element was this one. It's always the case anyway. And for the 80% of the variance for the wood density in our case, which is actually the pretty crucial or key wood fiber attribute for the lumber industry. So roughly what they did, the relationship between core and tree structure, core and plot structure, we did a lot of tree structure, evolved to reconstruct plot, and even now we have the possibility with this library of 3D models to reconstruct larger area like landscape. And the important thing I think to remember is we have 3 models, we would be able to have the best information on tree structure, but we also can tag any kind of attribute to each tree. So if we want to put a dollar sign on the tree, or attach carbon or biomass or something, we can easily map a large area with this fine scale information. If you need. That's it. Thank you.